Hello guys, welcome to my video. So today I'm going to be solving the May-June 2023 question paper 2-3 for physics, and the question paper is 1 hour 15 minutes long. So I'm going to be explaining how this paper was solved and how you can tackle some of the questions that are going to come, and how the questions have been worked out. So I hope you enjoyed the video. Please like if you like the video, comment if there's anything that is unclear, or if there's anything that you'd like me to improve on. Okay. So these are some of the data formulas that you often use, and some of the different formulas that will be asked. Okay, so let's begin. The first question is: a well has a depth of 36. Okay, so we're given a well that is a depth of 36 meters from the ground level to the surface of the water in the well. Okay, so a student wishes to find the depth of the well, and the student plans to drop a stone down the well and record the time taken from releasing the stone to hearing a splash made by the stone as it enters the water. So our student is standing over here, okay? And the student wants to drop a stone right here so that it reaches here, okay? And it reflects. So as it splashes, it makes a sound that then travels back to the student, and the student can then make a decision based on that. The student wants to calculate the time taken. The question wants us to calculate the time taken for the stone to fall from ground level to the surface of the water. Okay, so first of all, whenever you see graphs that has something to do with kinematic equations, it's very important for you to at least list down what you have been given. Okay, so we've been told that it has been released from rest, meaning that our u, okay, is equal to 0. Right, very important. And we've been told that this distance, so if the stone is at this point, okay, so this is our stone. If at this point it moves down to this particular surface of the water, it means that the distance that it has traveled, the displacement, is actually 36 meters. Okay, so the value of S is actually 36 meters. Right. What else do we want? Right. What else do we want? We also know that the value of G is actually 9.81, right? So having all these equations, you know that V squared is equal to U squared plus 2AS, S is equal to UT plus half AT squared, and V is equal to U plus AT. So depending on all those equations, you can select the one that best appeals to you, and the one that works. You have the distance, you have the initial acceleration, which is 0, and you want to find the value of the time itself. Okay, so we know that S, okay, so we know that S is equivalent to UT plus half AT squared, right? So the value of S is actually 36, and the value of U is 0t, right? Plus 1/2 times 9.81 t squared, right? And we want to find the value of that time itself, right? So the time will actually be 36, okay, multiplied by 2 divided by 9.81. The square root of that should be equivalent to our time. Therefore, our time is actually about 2.7 seconds, okay? 2.7 because the distance is actually to 2SF, right? So this is actually two significant figures, right? And the value of G might be 3SF, but the least value is the value of S with 2SF. So our answer should also have 2SF, okay? And we've been told that the time recorded by the student using a stopwatch is not equal to the time in A, right? So the student is standing up there, and the student has a stopwatch. So stopwatch is what we use to measure the time itself, but the student is not getting the time that is being calculated. Because remember, we are calculating the time that the stone is supposed to fall down, but the student is actually calculating the same time, but using a stopwatch, right? So there are many reasons why the time taken for the stone to reach the surface of the water is not even equal to the time that the student measures, right? There are many reasons. The first one that is most apparent is because of reaction time, right? So there is reaction time between, okay, hearing the splash, right, and stopping the watch, right, and stopping the stopwatch. Okay, hence time will be different, right? Hence different time, right? So because of reaction time, the time that the student measures using the stopwatch will not be equal at all to the time that the student is actually calculated. Because as the student tries to stop the stopwatch, right, if you're here, as the student tries to stop the stopwatch, the stone has already made a splash sound, and the student will not be able to time that correctly in order for him or her to stop that stopwatch, right? The other reason that is there is that the stone does not the sound rather takes time to reach the student, right? So the stone hits the water at a different time to the sound being heard. Okay, so the sound, right? The sound has to travel, right? So the sound has to travel to the student. Okay, so it takes time. It takes time to reach. Okay, so the student is actually at this point. So if you know sound, the time might be very small, but generally sound has to travel back to the student as soon as the stone splashes the water. That sound has to travel back to the student, and we're saying that the time is not the same. There's a time difference between the stone splashing the water and the stone sound being heard by the observer who is standing over there. So that is the reason why the time will not be equal to the stopwatch that will be there. Okay. The other reason that might be apparent. Okay. So if you think about this, right, we might talk of I would think of zero error, right? It's part of systematic error itself. To say a stopwatch somehow might have zero error, or it might not be calibrated enough. Remember, they just said suggest 3 possible reasons. It's not to say these are the actual reasons that are causing it, but you can just suggest anything that might work, right? So the stopwatch might have a zero error, right? Okay, so that is basically another reason why this will not be accurate, right? So maybe the stopwatch is already at 2 seconds by the time he or she wants to start the stopwatch. So because of that zero error, you won't be able to get the accurate reading that you want, right? There are many other reasons why this will not be the same. For example, the value of G is not exactly 9.81, right? Wherever you are, the value of G will not be 9.81. The value of G differs according to the place that you actually are. Another reason is the stone initial velocity will not be 0, right? It's going to be at a different initial acceleration velocity, because it's actually going to drop it at a certain velocity that we might not know, right? So you can't really say that initial velocity is actually 0, right? The stone might not follow a straight line. It might not travel in a straight line at all. It might move to the side, bend a little bit, and that will affect the equation itself, because that equation assumes that acceleration is in a straight line. But the time will therefore be different, because the displacement will not just be 36, right? It might be 36, but the distance traveled will actually be quite longer. That will be affecting the time itself taken for the stone to reach the water itself. There are many reasons. They really just wanted you to explain why these times would be different. Okay, move on to the next question. We'll be given a student that repeats the experiment 3 times, right? So this student is very clever, because he knows that in order for him or her to remove all the random errors, they have to take multiple readings and find the average. Okay, so I'm applauding them for that, because they knew that if they repeat the experiment 3 times, they'll be able to calculate the depth of the well. Okay, but we have to now see, is it really close to the true value? Are these values close to each other? So if we can answer those 2 questions, we can answer what you call precision and what you call accuracy. So basically, precision is how close the measured values are to each other, or basically the range of measurements themselves, right? Basically, that's precision. And accuracy is how close the measured values are to the true value. So you want to measure something, maybe the length of a table, and you find it's 10 meters, but the table is actually 20 meters, for example. It means that you're not accurate. You didn't get the true value itself, right? So you need to understand what precision is and what accuracy is. So if we're looking at these results, right, this is 54, this is 53, this is 54.1. Okay, so the first one that we can comment on, the first point that we can comment on is on precision, right? So these results are pretty precise, because the results, okay, or measurements are close to each other. Okay, are close to each other. So them being close to each other means they're really precise, right? So when I calculated their range, they had a range, okay, of 0.5, right? So the highest value and the lowest value actually had a range of 0.5. It's a very small range for values, and the average value of 54.1 was actually closer to all the values themselves, meaning they were quite precise, but they were not accurate, however. Okay, so very precise. It helped minimize random errors, but they weren't at all very good at minimizing the systematic errors. Okay, so they're not accurate. Why? Because the values, okay, or the measurements, okay, are not close to the true value. Okay, so we have a certain true value that we have, and these measurements are not close at all to the true value. So the examiners were looking for you stating that they're actually close to each other, that gives you the mark, right? And you stating that the results are actually not close to the true value, that gives you the other mark. Okay, so moving on to the next question. This is actually a question on forces, density, and pressure. So this is especially a question on upthrust. Okay, so let's work it out. So this is a question on upthrust, and we've been given a sphere that floats in equilibrium. Okay, so a sphere floats in equilibrium on the surface of sea water, right? 21% of the volume of the sphere is actually below the surface of the water, and we've been asked to calculate the density of the sphere. Okay, so whenever you see a diagram, try to analyze the diagram, understand what the diagram actually means. What does it mean to say something is in equilibrium? Well, this whole system has a certain weight that is acting down here, okay? But because it's in water, it's going to have a certain upthrust that will be acting upwards over there, right? So we have upthrust that will be acting up, okay? So upthrust acting up in that direction, and weight acting downwards, right? So the equilibrium is actually to say that the upthrust that is being caused by that is actually equal to the weight itself at that particular level, because those are the only two forces acting on the system. So how do you find the density? Well, we know that density, okay, we know that density is equals to mass over volume, right? So how do you find the density, and how do you find the weight itself? Okay, so the density is equivalent to the mass divided by the volume, right? But we know that upthrust is equals to rho g times v. But it's 21% of the volume of the sphere that is below the surface of the water. So 21%. So all of this, okay, all of this is basically 21%, right? So this is just 21%, meaning that this whole area above is actually what? The remainder of that is actually the one that is above, okay? So very important for you to be thinking of that. So the upthrust that has been caused by the water that has been displayed by that 21% of the volume is actually equal to the weight itself, right? So the upthrust is basically equivalent to rho times g times 21 over 100 multiplied by v. But the upthrust is actually equivalent to the weight. Remember, since it's in equilibrium, those two forces have to be equal, okay? So we can therefore say that the weight is equivalent to, but this is the density of the water itself, right? So this is the density of the water. This is the density that we're looking for. It's not the density of the metal, because with upthrust we're looking at the density of the liquid that we're actually displacing, okay? So we'll be saying the density of the liquid is actually 1050. So it'll be 1050 times the value of g times 0.21 multiplied by v. So that is the value of our weight itself, okay? But we know that weight is equals to mass times g, but weight is equivalent to m times g. Okay, so the mass of our object will actually be equivalent to that particular value, okay, divided by, okay, so this is our weight, sorry, divided by the value of g, right? So that is the mass of our object itself, right? So we have the mass, right? So these two cancel out. So we have the mass of the object. We now just want to find the density, right? So the density will be equivalent to the mass divided by the volume, right? The mass will be actually be 1050 times 0.21 v divided by the volume, which is v. Okay, so those two cancel out, and you'll be left with approximately 220 kgs m to the power of -3. So that is the value of our density, okay? Moving on to the next question, we'll be given a sphere that is now held so that its entire volume is below the surface of the water, okay? So the sphere is then released. Calculate the initial acceleration of the sphere. So we don't know what's holding up the sphere so that that volume is below the surface of the water. But we just know that the sphere is below the surface and the sphere is then released. So if we're looking at this, it's much more like that. Okay, so this is the surface of our water, right? And our sphere is down here, right? So this is our sphere, okay? And it's below the surface of the water, but it's held. We don't know by what. It might be a hand, right? A person maybe is holding the sphere. We don't know, right? So it's now held, but the entire volume is actually below the surface of the water. And then that sphere is released. And we want to calculate the initial acceleration of the sphere, right? So we want to find what is the initial acceleration that the sphere is actually moving with, right? Force is acting up is the upthrust, okay? And again, it's the weight, right? So the word initial means that initially the upthrust is greater because this has to go back to the surface of the liquid, right? This thing has to rise up because the weight is very small. If you look at the first question, it was actually almost suspended. Just a fraction of the weight itself was overcoming that amount of upthrust, right? So the upthrust is very, very big. So as we push the object down, there's going to be an initial velocity that is going to be due to the upthrust itself, right? So the acceleration will be due to that initial upthrust. So the difference in the upthrust and the weight is actually going to be our resultant force, okay? So we know that the resultant force is equivalent to the mass times the acceleration. So the upthrust, which is going up, minus the weight acting downwards, should be equivalent to the mass multiplied by the acceleration, okay? But we know that upthrust is equal to rho times g times v. If we were to subtract the weight, we're going to end up with the mass multiplied by the acceleration. But how do we calculate the weight? Well, we know that this thing is acting upwards, right? We know that weight, okay? We know that weight is equivalent to the mass multiplied by the value of g. But the mass, we already have it. We've already calculated the mass from this expression, right? Our mass is already 1050, which is already 220 multiplied by g, because we already have 1050 multiplied by 0.21 times that, multiplied by the value of g, multiplied by the value of v. So our velocity, our volume multiplied by this mass, because the expression for the mass is 1050 times 0.21 multiplied by v. So multiplied by g, this whole becomes the expression for the weight itself, okay? So minus the weight, which is 220 gv, that would be equivalent to our mass times our acceleration, right? But we know that the density itself is 1050 multiplied by the value of g multiplied by v minus 220 multiplied by g by v will be equivalent to our mass multiplied by our acceleration. So we just want to find this particular value of our acceleration, right? So if we were to take this calculation down, we get about 830. Okay, so if we were to subtract this, that's about 830 GV. That would be equivalent to the mass that we have. Remember, our mass is usually 1050 times 0.12 V. So it would be over 220 V, right? So multiplied by the acceleration, that is actually the value of our acceleration, right? So acceleration will be 830 times 9.81 times the value of V divided by 220 gives us an acceleration of 37 meters per second, okay? 37 meters per second, okay? Very important. So just remember this, we have upthrust acting on the system and we have the weight which is acting downwards, right? So the upthrust moves up, the weight moves down. Initially, the upthrust causes the ball to move up. So a ball is going to be somewhere over here. It's going to keep on moving up until it reaches to the surface itself, right? So as it moves up, it's because of the upthrust that is opposing the weight. So the initial acceleration will be the upthrust minus the weight, right? So you manipulate your values until you find the value of your acceleration. Very important. So we've been given the sphere that accelerates upwards but remains entirely below the surface of water. You've been asked to state and explain what happens to the acceleration of the sphere as its velocity begins to increase. So I want to introduce a concept of what we call, okay, viscous drag, right? So viscous drag force. It is a force that basically acts in all liquids, right? Because of the friction that exists, okay? So if you have a liquid, and an object in the liquid itself, okay, as the object moves upwards in a liquid, right? So as your object moves up in that direction, right, actually the drag force will be moving in the other direction, right? So the value of your drag force will actually be in the downward direction. So as the object moves up, the drag force is down. As the object moves down, the drag force is always up. So those two forces are always affecting each other. But remember, the viscous drag force actually increases with increase in speed, right? With increase in speed, the viscous drag force actually begins to increase. So it's very important for you to be thinking of those two aspects, right? So we can really just talk about that. And as the viscous drag force increases, the total resultant force decreases. And since F is equals to ma, as the force decreases, the acceleration will therefore decrease. Okay, so we just talk about that. So as the downward drag force increases, okay, increases with speed, okay, the resultant force actually decreases, right? Why? As upthrust, okay, as upthrust and weight remain the same, okay, remain the same. Therefore, the acceleration, okay, therefore the acceleration actually decreases, right? Okay, so just think about that. So the downward drag force actually increases as the speed increases. The total resultant force begins to decrease, and the weight and upthrust basically remain the same. Therefore, the acceleration will begin to decrease. So whenever you hear the word what happens to the acceleration, think of the force. What is happening to my resultant force? And that will guide you in explaining what happens to the acceleration itself. Very important. So I've been asked to state the principle of conservation of momentum. So basically, this is the sum of the total momentum. Okay, the sum of the total momentum before collision, right, is equal to the sum, okay, of the total sum of the total momentum after collision, okay, provided there is no external resultant force. Okay, there is no external resultant force. So the 2 marks basically are from you stating the sum of the total momentum. So the total momentum before the collision is actually equal to the sum of total momentum after the collision. So that's your first mark, right? And the second mark then comes from saying that there is no external resultant force, right? Some people might say that it's an isolated system, right? So if the system is not isolated, that momentum will not remain the same. Okay, very important, right? Moving on to the next one. We've been given a firework that was initially at rest. So initially we had a firework that was over here, right? So basically this was our firework, right? So it then exploded into different fragments, fragment A, fragment B, fragment C, right? So all moving in different directions. And we've been asked to calculate the angle theta that fragment C moves with. So we give fragment A with a mass of 33 meters, right? Fragment B, mass of 2, and fragment C with a mass of m, okay? So we want to find the value of the angle theta, right? So I want you to understand this with regards to momentum at angles, right? Momentum in the y and momentum in the x is conserved. So momentum is conserved in both directions, the x as well as the y. So it's very important for you to be thinking of that. So we've been asked to calculate the value of the angle theta. So ask yourself, what direction are you going to be considering? So as for me, I might consider momentum in the x, right? So consider both of that. So considering momentum okay, so considering momentum in the x direction, we know that the initial momentum is actually 0 because nothing has moved, right? Before the collision, the actual initial momentum was actually 0, and then after the collision itself, right? So this is the horizontal. One of the horizontal is this one. Then the other horizontal is this one resolved, right? So if we were to resolve this, this actually becomes V, okay, sine, right? So it actually becomes V sine, because it's actually this angle, and we want to find that, it actually becomes V sine of theta, right? So very important, which this is the cos, right? So this is V, this is actually V cos theta, right? And that is V sine theta, right? So you have two of that. So momentum in the Y, momentum in the X direction is actually 6 times 2 meters, right? So this 6 and that 2 meters acting, momentum in the X is actually this 3 times that 4 meters, okay? So 3 times 4 meters, right? Subtract the momentum that would be in that direction, right? Which is mv sine theta, is mv sine of theta. So the momentum here will be 12m, okay, is equivalent to mv sine theta. So v sine theta will actually be equivalent to 12. So we just keep that in mind and we'll apply that pretty soon, right? We go on to momentum in the Y. So basically when you see momentum at an angle, you have to ask yourself these questions. What is the momentum in the Y direction, and what is the momentum going on in the X direction, right? So for the momentum in the Y, we're going to say initial is 0, right? So we have 6 and 2 there, right? So 6 multiplied by 2m, we subtract, right? So in here it's actually mv cos theta, right? We subtract mv cos theta, so 12m is actually equivalent to v cos theta, right? So v mv, so v cos of theta is actually equivalent to 12, right? So we now know v sine theta is equal to 12, and v cos theta is actually equivalent to 12, right? So what do we do with all that information? We then say, if we divide these two equations, if we say v sine theta, which is equivalent to 12, divided by v cos of theta, which is actually also equivalent to 12, this cancels out. We're left with sine theta divided by cos theta, which will be equivalent to 12 over 12, right? But if you've done trigonometry, you know that sine theta over cos theta is actually equivalent to tan theta. So your value of tan theta is actually equivalent to 12 over 12. So your value of theta is actually equivalent to arctan of 1, which is equivalent to 45 degrees, okay? So your answer becomes 45 degrees. So what were they looking for? They were looking for your answer, the answer that you gave, okay? And they were looking for momentum in the X, and they're looking for momentum in the Y. So it's very important for you to be thinking about this. Ask yourself, what is momentum in the X? What is momentum in the Y? And what can we find, right? So the only tricky part here was on the value of sine theta and cos theta. Understanding that in mathematics, sine theta of the cos theta is actually equivalent to tan theta, right? But they always ask you to actually understand trigonometry for some questions that you will be solving, okay? I'll move on to the next question. We've been asked to then calculate the value of the speed v. Okay, so if we look at the momentum in the Y, right, let's go back to our momentum in the Y, and we're given mv, 12m is equivalent to mv sine theta, right? So we know that from that equation, 12m is equivalent to mv sine theta. So if that cancels out, that means 12 is equivalent to v sine of theta. So v is actually equivalent to 12 over sine of 45, right? So basically, that is something that you should be thinking about. And if you punch that in a calculator, that gives you an answer of 16.97056, which is approximately 17 meters per second, right? So your answer is 17. So they're looking for you applying one of these things that you know, and then determining the value of V, okay? Moving on to the next question. We've been told that the fireworks contains a chemical that is mass of 5, and that is the energy per unit mass of that, right? So we know that 1 kg, okay, so 1 kg, we know that 1 kg is actually equivalent to 700 joules of energy. So what about 5 grams, right? So 5 grams will actually be equivalent to less, okay, so less that amount of energy. So 5 over 1000 divided by 1 multiplied by 700 will actually be 5 over 1000 multiplied by 700. That will be equivalent to about 3.5 joules, right? So if 1 kg is equivalent to 700 joules, 5 grams has to be equivalent to less. So therefore we can find the value of that amount of energy that we have, okay? Moving on to the next question, we've been asked to then calculate the value of the mass m, right? So very important for you to be thinking about how this mass is going to work out, right? So basically we know that the kinetic energy. So since it's going to explode, we know that the kinetic energy, so EK, right, for all particles, okay, so for all particles, will be equivalent to the chemical energy, right? So that will be equivalent to the chemical energy that is available, right? So let's look at the kinetic energy for each of these particles, right? So for the first one, it's actually half of 2m multiplied by 6 squared, right? Plus, for the other one, it's half of 3m multiplied by 4 squared, plus, for the other one, it's actually half of m multiplied by 17 squared. That should be equivalent to the value of 3.5 that we have. And we know that 36, right? So that gives us 36m plus 24m. The other one gives us 144.5m. That should be equivalent to 3.5. So overall is 204.5m is equivalent to 3.5. So the value of m is actually 3.5 divided by 204.5. So the mass of our object will actually be 0.017 kilograms. So that will be 0.017 kilograms, right? So just be thinking about that. The kinetic energy of all that particles is actually coming from the chemical energy that is stored. So as it spreads apart, it's going to spread away all that energy into its near surroundings, okay? So the next question that we'll be answering is a question on waves, okay? So very important topic, right? So let's begin. We've been asked to define what is meant by the frequency. It's a 1-mark question. So frequency is basically the number of oscillations, right? So the number of oscillations, right, per unit time, of a point on the wave, right? So how many oscillations in a given period of time does a particle on that wave complete per given time? Basically, that is what we call frequency, right? The next question, we'll be given a loudspeaker, okay? So this is our loudspeaker, and we'll be given a microphone and a cathode ray oscilloscope, right? And we've been asked we've been asked to calculate the frequency of the sound wave, okay? So if you look at the question, we're given the time base to 0.50 times milliseconds per centimeter, and we'll be given the Y gain to 0.20 volts per centimeter, and we've been asked to calculate the frequency of the wave. So basically, we know that the frequency is actually 1 over the period that you have, right? But the value of a period t is equivalent to what, right? So it's equivalent to the number of divisions, right? So the number of divisions multiplied by the time base itself, right? So that should be equivalent to the value of our period itself. How many divisions do we have, right? So if we were to look carefully, if we look at this particular point itself, right, in that particular point itself, which is about 1 wavelength apart, and also look at that one point, and that other point is also 1 wavelength apart. This is actually 1, okay, and that from here to there, it's actually 2. From there to there, it's actually 3. From there to there, it's actually 4. So we have about 4 divisions, right? 4 divisions. What is the time base? It's 0.50 per division, right? So 0.50 times 10 to the power of -3, right? Milliseconds, right? So our frequency will actually be equivalent to 1 over 4 times 0.50 times 10 to the power of -3. That is basically equivalent to 500 hertz, right? So very important, equivalent to 500 hertz, right? The next one, we've been asked to calculate the amplitude of the signal received by the cathode ray oscilloscope, right? So basically, the amplitude is related to the Y gain itself. So this Y gain tells you basically the voltage. How do you find the time gain? The Y gain, basically, we look at this particular. So how do you find the Y gain? So how do you find the Y gain? We look at the divisions in the Y axis, right? So from this point, it's actually 1, 2, 3, 4, 5. That's 1 centimeter. 1, 2, 3, 4, 5. There's another 1 centimeter. So we have 2 centimeters, right? So 2.2, 2.4, 2.6, 2.8. So basically that's 2.8 centimeters because each box represents 0.2 centimeters. So basically we have 2.8. So our amplitude is actually equivalent to, so our amplitude is actually equivalent to 2.8 multiplied by 0.20. That gives us a total value of 0.56 volts, right? So it's 0.56, which is the value of our voltage. So Whenever we talk of the amplitude of the signal, we have to look at the Y gain. What is the Y gain that we have? And we have to look at the voltage that we're given. Then we can find the amplitude that we want to find. The next part of the question, we've been given the intensity of a wave reduced to a quarter of its initial intensity. So I highly recommend that you watch my video that I posted about polarization and Malthus's law. You can check in my channel and you can be able to understand really what is intensity and how does intensity come about. But I'm going to be answering this question, but it's very important for you to watch it and even watch some of the questions that I've solved surrounding intensity itself so that you can be able to get a feel and understanding of how these questions might be solved. But basically, what this question requires us to know is that intensity is directly proportional to the amplitude, right? So very important for you to know that the intensity is directly proportional to the amplitude squared. Therefore, intensity is equivalent to Ka squared, right? But the intensity is reduced to 1/4 I. So it's reduced to 1/4 I, but that is equivalent to A2 squared. We want to find that new intensity, that new amplitude, that has been caused by that decrease in the intensity, right? So this is our first equation, and this is our second equation. But the value of K is equivalent to I over A squared, right? So we can substitute that in that equation. So we have 0.25 I being equivalent to I over A squared multiplied by A2 squared, right? So we have 0.25 I multiplied by A2 squared, right, is equivalent to I A2 squared, right? So, multiplied by A squared, right? Just A. So this cancels out. So our new amplitude is actually the square root of 0.25 A squared. So our new amplitude is actually 0.25 multiplied by A. So it's really a certain fraction of the original one that we have, right? And the square root of that, which is equivalent to 0.5 times A, right? But the initial amplitude is actually 2.8 centimeters, right, which is 0.56 volts. But now it has been reduced to half of that because of our effect of decreasing the intensity. So it will be actually 0.50, right? So it will be 0.5 multiplied by 2.8. Basically, that gives us about 1.4. So basically have 1.4 being our new amplitude that we have from 2.8. But one important thing, there is no change in the frequency. So the period remains the same. So the first marking point, they want to see, do you know the amplitude itself? So for you getting this correct amplitude is actually an A1 mark that you get. But it's dependent on a certain method that you're going to do. So your method is you're going to draw a sinusoidal wave. Okay, so you're going to draw a sinusoidal wave, right? That is amplitude that is less than 2.8 throughout. Okay, so this is going to get you your M1 mark, and your A1 is coming from the amplitude itself, and the last one is just a B1 mark. They're just going to give you, because you have calculated the same period, right? So not calculated, rather, it's the same period throughout, right? If your period is the same, they're going to give you that B1 mark. So those are the 3 marks. They're going to look at your amplitude. They're going to look at, is it a sinusoidal wave that is less than 2.8 throughout? Then they're going to look at the period. Is it the same period throughout? Okay, so if we were to go through here, we start at this point, right? So the amplitude is supposed to be 1.4. So initially, we had this particular point that was there at the top, and we want to put it somewhere here. So basically, it was at that point. So it's going to go down to 1.4. So this is 1 centimeter. 1, 2, 3, 4, 5. So basically, it's going to go down to somewhere here, right? Somewhere like that, right? So this is 1 centimeter that will be there, and this is 1.4 centimeters that will be there, right? So the same will happen even here, right? So it will be 1 centimeter. So 1 centimeter is basically somewhere there, and 1.4 will basically somewhere there. The same will happen here. This point here will move to 1.4. So basically, this is 1 centimeter over there, and this is basically 1.4. The same will happen to that point, right? And so on and so on and so on, right? So basically, 2, 4, 5 here. So basically, this point will move to that point will move to that point, and basically that point will move to that point, right? So this is the new wave that we'll be drawing, but that wave is going to have the same frequency. So it's going to cut at the exact same points, right? So we're going to start with our wave, it has to cut at the exact same points, right? So wave is going to go here, it cuts through that point, it cuts through that other point, it goes, it cuts through that point, cuts through that point, goes, it cuts through that point, and it reaches there, right? So basically they just want a sinusoidal wave that is the same period, it cuts through those exact same points, but its amplitude is basically just way less throughout the whole motion of your wave. Okay, moving on to the last part of our wave, we've been asked to state the principle of superposition, right? So the principle of superposition basically says when two waves, okay, so when two waves meet at a point, okay, so when two waves meet at a point, when two waves meet at a point, right, the resultant displacement, right, the resultant displacement is the vector sum, okay, the vector sum of the individual displacements, right? So you have individual displacements that are occurring, and when those two waves meet at a point, the resultant displacement that you get is actually the vector sum of the individual displacements that you're going to get, okay? So the initial position on the microwave is such that the trace on the CRO is an amplitude minimum, right? So basically, you need to get this, right? An amplitude minimum refers to what we call a node, right? So an amplitude minimum basically refers to a node, but an amplitude maximum basically refers to an antinode, right? Very important, right? What is an antinode? An antinode is an area of maximum displacement, and a node is an area of minimum displacement on a stationary wave, right? So as the microwave moves, it's going to pass through three specific points that have an amplitude maximum before it reaches a point where it has an amplitude minimum. So we're going to start at an amplitude minimum. So whenever it is starting, it's going to start at a node that will be over there. But it's going to pass through 3 points that have an amplitude maximum. So it's going to pass through an antinode, going to pass to another node, and then another antinode before reaching to a node, right? So before it reaches to a point where the amplitude is at. So if we look at this, we have a node, an antinode, and a node would therefore be in between a node and then another node, right? So we have a node in here, okay? So if we were to put it much better, okay, so let's draw this. So that it's much easier to see. So we have a node here, then we have an antinode that is present over there, then we have another node, then an antinode, then a node, then an antinode, then another node, right? So we have a node to a node, and that's basically 1 lambda, and a node to an antinode, that's basically half lambda. So you need to get this, right? To move from a node to a node, that's basically half lambda. A node to a node to another node, right? So this distance is basically lambda. An antinode to another antinode is also half lambda. An antinode to a node is actually 1/4 the value of lambda. So you need to be knowing these particular facts. They come in handy when making a lot of questions of this. So we have a node to a node, that's 1 lambda. An antinode would be lambda. So in total, the wavelength would therefore be 3/4 lambda. Okay, so the separation, okay, so the separation is actually equivalent to 3/2 the value of lambda. But separation here is 1.05, which is equivalent to 3/2 lambda. So 1.05 multiplied by 2 divided by 3 is actually equivalent to your value of lambda. So your value of lambda will be equivalent to 0.70 meters. So 0.70 meters. So very important, right? Just know the fact that from node to a node, it's half lambda. From a node to another antinode, skipping a node in between, that's a whole lambda. You just find your distance and you have the values that you're looking for. The last question, we've been asked to determine the speed of the sound. We know that V is equivalent to F lambda. So the value of our V will actually be equivalent to what's our frequency. We've calculated in the initial question and we've gotten an answer of 500. So we go with that answer here of 500 and you multiply by the lambda that we've calculated, which is 0.70, and that gives us an answer of 350. Okay, so what are they looking for, guys? They're looking for this equation, which is a C1 mark, and that equation, which is an A1 mark. So if you just give this equation itself, you've gotten yourself a full mark, and if you just give this particular correct answer itself, you've gotten yourself another mark. So very important for you to be thinking about what they're looking for. It doesn't matter if you know the values, but if you don't put the equation in physics, the equation is very important. Okay, moving on to the next question about electricity. We're almost done. We've given a student, we have set up a stationary wave with a battery, okay, an ammeter, a heater, and an LDR connected. All of them are connected in series, right? So they just want us to create that circuit. They just want us to see if we really understand some of the circuit symbols that are out in the syllabus. So if you look over here, I've posted some circuit symbols that I really hope are helpful as you'll be working some of these questions. So if you like them, I'll recommend that you copy them down and you'll be able to read them and understand how they work. But basically, I know that the circuit symbol for heater is basically something like this, right? So a heater basically is a circuit symbol. We have 1, 2, 3, 4, right? So we have basically 4 compartments that are sort of like in a square box, right? So one of the ways that I got this was just to say the word heat itself has 4 letters. So we must have 4 boxes that will be present in a heater. I don't really know if it is very important for you to put exactly 4 boxes, but I highly recommend that you give the symbol as it is. For example, an LDR basically is like that, and there's 2 lines passing through it, which is basically showing light being emitted on it. So I'm not quite sure if you put 3 lines, you'll be still marked. But basically, it's much safer to just give the correct symbol as it is given in your syllabus and as it is given in your questions as they come, right? So if we're to finish this, we're drawing over here, okay? And we're putting here, we're putting our ammeter. If you go over here, we're putting our heater. So it's 1, 2, 3, 4, okay? So let's put our compartments here. So we're going over to this circuit, okay? So we have 1, 2, 3, 4 compartments. Then if we were to go here, we have our light dependent resistor. So a light dependent resistor, something like that, that's dependent on light, okay? Then we go back to our circuit, and across here we have connected a voltmeter, right? So a voltmeter is in parallel, right? So basically this is the kind of circuit that they're looking for. So the first 3 marks, so what are they looking for? The first 3 mark is for the correct symbol, right? So the first mark that you'll be getting is for the correct symbol. So if you're given a correct symbol, you get that mark. And then all symbols must be in series. Do you know what series means? And then you get your other mark. Then the last mark, well, basically, do you know the symbol for the voltmeter? And do you know what it means to say that it's in parallel? What is a parallel connection? If you give all of that, you'll be able to get your mark. So this is your parallel connection. This is your correct sex symbols, and you'll be able to get your mark, okay? Moving on to the next question. We've been asked to calculate the resistance of the resistor. We've been given the voltmeter reading, and we've been given the resistance basically. So if you want to find the resistance, we know that the resistance is actually rho L over A. So basically, that is one of the equations that they'll be looking for when they're looking at this particular question. So we know that resistance, okay, is equivalent to rho L divided by A. So the value of your resistance, what is your resistivity? 1.1 times 10 to the power of -6. Your length is 2.0. Your area is 3.8 times 10 to the power of -7. You get your answer of 5.8. What are they looking for? They're looking for this formula. Just give the formula before you start making any calculations, right? Then you can make your calculations and get your answer. But first, give the formula whenever it is required, right? So this is 5.8. The reading on the ammeter, right? What do we know? We know that for a circuit, the voltage is equivalent to IR. How do we know this? We know this from Ohm's law, right? So it's basically Ohm's law that says that the voltage passing through a component is directly proportional to the resistance, provided that all other external conditions remain the same. So the the potential difference across a component is directly proportional to the current actually flowing through it, provided that temperature and other external factors remain constant, right? So basically that is Ohm's law. I mean, you can find the value of R by actually saying V over the value of R itself, right? So you can find the value of I by saying V over R. The value of our V is actually 4.8, okay? So 4.8 divided by 5.8, that will be actually equivalent to 0.83, right? So 0.83 becomes our reading on the ammeter. Very important. The last question, we've been asked to we've been told that the heater is replaced by a new wire, okay, that is the same length but a larger diameter, right? And we also state and explain whether the new wire is a resistance that is greater, okay, less than, or the same as that of the wire in question B. So what is happening? We have the same length, but there's a larger diameter. So what is the effect of that diameter? Well, if we were to look at a normal cell, so I'm going to be explaining how area and how length affects resistance, right? So the first one is if you look at length, right? How does length affect resistance, right? So if length is like that, so let's consider this as rod A, and let's consider this as rod B. Okay, so they have the same area, but what's different is the length, right? So we know that length is directly proportional to the resistance, right? As length increases, okay, as length increases, the resistance actually increases, right? So I can give you a simple analogy. Imagine these are multiple people that are present in a hallway, for example. You want to get from point A, okay, from point A up to point B, right? And there are multiple people across it. So if you're a person who's standing over there, you're obviously going to encounter more people to get to A, right? So those people might represent the resistance itself. So as charges are moving from point A to point B, if it's longer, they experience more resistance itself. So if it's longer like this, there are now multiple people and they're going to experience long resistances. So you're going to experience, if you're here, you're going to experience a greater resistance as you move from point A across point B, okay? So that is the effect of length. As length increases, the resistance actually also increases. But if we were to look at area, how does area affect resistance? Well, if we look at area, if area is like that, so consider some that with area A, okay? Then consider something like that with area actually 2A, right? So as area doubles, it means that the resistance actually decreases. So resistance is proportional to the area. Again, imagine our analogy. You're standing here at point A, you want to get to point B, right? So you're standing here, so you're standing at point A and you want to get to point B. So you're going to encounter again similar same number of people, but if those same number of people remain the same, but the area is made now much bigger, as you're standing over here, the resistance is going to be less. You can easily just walk through parts of them because they are more spread apart. So as area increases, the resistance that charge faces actually decreases, right? So you should be thinking of that. As the diameter is larger, what effect does it have? A larger diameter, what happens to the area? I know that area is similar directly proportional to d squared, right? So as area increases, right, as diameter increases, the area is larger. As diameter increases, the area is larger. So we have a larger area simply because the diameter itself is actually increased. So the diameter has an effect on the area that is present, right? So as the area becomes larger, the resistance decreases. So R for the new wire, okay, so R for the new wire, is less, right? So very important. The last question, we've been asked to state and explain whether the new reading on the voltmeter is greater or less than equal to R, okay? So think about this, right? The resistance decreases. So the resistance across the heater is actually decreasing, right? What does this mean, right? It means, so it has a smaller proportion, okay, smaller proportion of the total voltage, right? So the total voltage that is there, it will have a smaller proportion, right, of that total voltage. So the voltage reading, so the voltmeter reading is actually less than 4.8. What do I mean by this? Well, one of the interesting things about current is that whenever we have a circuit, resistance actually determines the voltage that is distributed, right? So what do I mean by this? Well, electrons deposit energy when they move in a circuit, right? We can agree. If I have a basic circuit like that, right? I have resistor R1 and I have resistor R2 and I have resistor R3, right? So basically my circuit is going to deposit energy across these different resistors, right? So R1, R2, and across R3. But energy is distributed on the basis of the resistance itself. So a simple example to understand this, so it's sort of like a potential divider formula. right? So a simple way to understand this, imagine I have a packet of sweets, right? So I have a bag of sweets that I have over there, and I want to distribute it amongst 3 people. Okay, I need a criterion. I can't just distribute them randomly. I could say the eldest one gets more sweets, the least gets less, and the smallest one gets like 1 sweet, right? So I've decided to have a criterion on which I can distribute the sweets that I have, right? So for current, resistance is acting as that criterion like age. It restricts. The bigger the resistance that you have, the older that you are, the more the number of the energy that you have, right? So if the resistance is decreasing across this heater for a new one, it means that the proportion of the total voltage that it gets will be less. So its voltage will be less than 4.8, right, of the previous one. Very important. We're almost done. We've been asked the last question to define the Young modulus. So the Young modulus is basically the stress to strain ratio, right? Moving on. We've given a uniform wire supported from a fixed support point. Masses are basically then added on the other end of the wire. The variation of the length L of the wire and the force is actually applied. Okay, so the cross-sectional area of the wire is that, and we've been asked to determine the unstretched length of the wire. So basically, before the wire is stretched, it's this one, right? So it's unstretched because the force is 0, right? A 0 force means that it's unstretched. Hence, that is where it is unstretched when we haven't applied a certain force. So the unstretched length will be 1.998, right? So the unstretched length will be 1.998, right? The next question, we've been asked for as an applied force of 30 newtons, determine the stress. We know that stress is equivalent to the force divided by the area, right? So the force is 30 and the area is 0.95 times 10 to the power of -3 squared, right? So whenever you see the word millimeter squared and you want to convert it to meters squared, you know that millimeter is 10 to the power of -3, and if you square that, you get 10 to the power of -3 squared. If it was centimeter squared, right, if the question might have said centimeter squared, you just say 10 to the power of -2 squared. You get your answer in meter squared. If the question says decimeter squared, it's just 10 to the power of -1 squared, right? So basically that's what you do if you just want to have area conversion, right? So that gives you a value of stress to be approximately 3.2 times 10 to the power of 7. 3.2 times 10 to the power of 7, right? The next one is strain. Strain is actually the ratio of the extension, right? So the extension over the original length, right? The extension divided by the original length. So the extension you'll be looking at, for example, in this case at 30, the length, so at 30 is over here, the length is actually 2.003. So at 30, imagine if 30, the length is almost like that. So its system is almost like that, much longer. So this is actually 2.003. So the extension is actually, the extension E is actually 2.003 subtract 1.998, which is actually 0.005. Get this. So it will be 0.005 divided by the original length, which is 1.998. So a strain is 2.5 times 10 to the power of -3. 2.5 times 10 to the power of -3. Okay, I'll move on to the last question. It's a question on flavors of quarks, right? So basically, they just want us to give the symbols for the charges and of the different quarks that you have, right? So an up quark basically has +2/3, but an anti-up quark, an antimatter basically has the same charge but opposite mass of normal matter. So its charge is going to be -2/3. Down quark actually has -1/3. Anti-down will be +1/3. Charm will be +2/3. And anti-charm will be -2/3. How do you know that it's actually 2/3? An easier way that you can cram this is actually charm and strange, right? So the word strange is the word N, the letter N in it, right? So that N actually stands for negative, right? So it means it's the only one which has negative, so it's -1/3, and charm will be +2/3. So those two work hand in hand, right? The next one, we've been asked to give a possible combination that gives a neutral bion. A combination that gives a neutral bion. What is a bion? Well, a bion is basically something that contains 3 quarks, right? So a bion basically has to contain 3 quarks. Okay, but a meson, right? But if meson has to have 2 quarks, okay, one of them has to be a normal quark And the other one, so basically this is our meson, and the other one has to be an anti-quark, right? So basically that is what makes up a meson, and that is what makes up a baryon. So for it to be neutral, we need three things, three quarks that will give us a total answer of 0. So we can have an up, a down, and a down. So imagine you have 2 over 3, you subtract 1 over 3, you subtract 1 over 3, you basically get 0. A meson, remember, has 2 quarks, so we need an anti-quark and then a quark. So we can have an up quark and an anti-down quark, right? So an anti-down quark, those two we add up. An up quark is actually 2 over 3, anti-down is 1 over 3, that adds up, that gives you an E, right? 2 over 3E, 2 over 3E, that gives us your answer, right? An up or anti-down. It can also be a charm or an anti-down, right? So in charm quark and an anti-down can also give that answer. Even here, it can be a charm as well as a down quark, as well as another down quark, right? So very important to be keeping that in mind. So quarks are basically part of fundamental particles. Electrons, however, are part of a group of another fundamental particles, and those particles are known as leptons, right? So basically leptons, these are particles that do not experience a strong nuclear force. So leptons do not experience a strong nuclear force, right? Do not experience a strong, nuclear force. Why? Because they're not found in the nucleus. They're found in the shells. They are found outside of the nucleus. But the opposite of them are actually hadrons, right? These are basically protons or neutrons, right? And these are found inside the nucleus of an atom itself. And the other name of the particle that belongs to this group also is the positron, right? Basically all other particles that are outside, the positron, the neutrino, or the anti-neutrino. Okay, so all of that basically fits into those particles that are there. Okay, so we're basically done. I really hope you liked the video. If there's anything that is unclear, please comment so that I can be able to address that. So basically these are part of the questions that come. So the last question is basically about atomic physics. In this case, we had a bit of deformation of solids, electricity, waves, upthrust, forces, density and pressure, conservation of momentum, and physical quantities and kinematics, right? So basically they try to cover the whole syllabus when they're asking paper 2 questions. So it's very important for you to revise and be able to understand. Thank you for watching. I'll see you in the next one.